Good evening, sir.
Hi, good evening. Actually, am I audible? There is a little bit of
Yes, sir.
disturbance. Yeah. Okay. Okay. Then let's wait a couple of minutes. Then we'll start. So, do you have any doubts from last class, or everything was clear? So, are you guys enjoying these live sessions, or it is kind of boring?
Yes, sir.
Okay. Okay, so let's start, then others will join gradually. Okay, so today we'll be solving another 3 questions from 2019 chemistry paper. Question number 46, 53 and 55. And after that we will discuss a little bit about the adsorption on the solid surface. If time is left, then we can discuss. Okay, so let me just share my screen. Okay, so first again introducing myself. My name is Shubhadeep, and I am doing my PhD at IIT Kanpur in the theoretical chemistry, in the topic of theoretical chemistry. Okay, so this is my second year going. Okay, so let's start. So this is question number 46 from 2019 paper. And the question says the specific rotation of optically pure R enantiomer of 2-bromobutane is -112.0, and a given sample of 2-bromobutane exhibited a specific rotation of minus 82.88. So we have to find out the percentage of S enantiomer of 2-bromobutane present in our given sample. So basically in this question the specific rotation of R enantiomer is given, which is minus 112.0, and the specific rotation of a given sample containing the 2-bromobutane is also given, which is the observed rotation, which is minus 82.88. Now we have to find out the percentage of S enantiomer present in the given sample. Okay, so first just look at the let's understand the what is the concept of specific rotation and optical rotation. So specific rotation is basically the change in orientation of the plane of polarization when we pass a monochromatic plane polarized light through a sample. Okay, so the concept is basically in a sample tube we generally keep our sample containing a compound, organic compound, let's say 2-bromobutane, and we pass a monochromatic plane polarized light. So monochromatic means single wavelength. So that means there is no mixture of wavelength, so only single wavelength is there. And plane polarized light mean the light electric field vector is oscillating in a particular plane only. That means let's say in a 3 axis, let's say it is x axis, it is y axis, and it is z axis. So we know that the electromagnetic field is composed of electric field and the magnetic field. So in unpolarized light, the electric field vector is oscillating in every possible direction. Yeah. In the case of unpolarized light, the electric field is oscillating in every possible direction. But in case of polarized light, that means the electric field is oscillating just along one particular plane. So let's again draw 3 axes. Let's say this is x axis, this is y axis, and this is z axis. Now let's say the electric field is moving along the y direction, and the electric field vector is oscillating like this. That means here in this case of plane polarized light, the electric field vector, that means this vector is oscillating along yz plane. So if you consider this yz plane, so the field vector is oscillating along yz plane. So this is why we call it plane polarized light. That means the light is only polarized along one particular plane. So now now if we pass this monochromatic plane polarized light along the sample tube, if our sample contains any chiral compound, then the sample actually the given solution or compound actually changes the orientation of the plane of polarization. So gradually it actually changes the orientation of plane of polarization. So the degree of rotation of plane of polarization of our incident electromagnetic field or plane polarized light, we call it the specific rotation. So degree of orientation or degree of rotation is called the specific rotation. Now why the chiral compound actually show this type of property, I will not go into the detail. So if you want to know, just let me know. So this specific rotation or optical rotation or the rotation of plane polarized light is actually a property of chiral compound. So this is why we call the chiral compound is an optically active. Now this rotation can be actually of 2 types. One is the dextrorotary and another one is levorotary. So dextrorotary means the compound or chiral compound rotates the plane of polarization clockwise, in the clockwise direction. Or levorotary means that it rotates the plane of polarization in the counterclockwise direction. So one we consider plus and another one we consider minus. Now the optical rotation is measured with a polarimeter instrument, and for any given solution, so optical rotation is represented or is expressed by this expression. So this is optical rotation, and with subscript lambda. Lambda is the wavelength of our incident monochromatic plane polarized light. So this is the wavelength. Now let's say if we use the sodium D light, which is commonly used. So sodium D light, the lambda is 589 nanometer, and the superscript T is the temperature of our solution. Now here alpha is the observed rotation, that is the observed rotation of our given solution, and L is the path length, that means the path the length of a tube containing the solution in decimeter unit, and the C is the concentration of our solution in gram per ml unit. So this is the expression for optical rotation. Now enantiomeric excess or optical purity. So what does this mean actually? Now we want to know how much our sample how much the purity of our sample is. That means the quantity or amount of one enantiomer present over another. That means let's say our we have a solution here, and we want to know the percentage of one particular enantiomer, let's say percentage of R enantiomer present in this solution over another, that means the S isomer. So this is called the optical purity. That means how much optically pure our sample is. So the enantiomeric excess or optical purity is expressed by this expression, which is the observed rotation, the ratio of observed rotation and the specific rotation of pure chiral compound. So let's say we have a in this case the given solution is 2-bromobutane. This is the solution, and we know the observed rotation here. That means the solution actually rotates the plane of polarization by minus 82.88 degree, and we know the specific rotation of pure chiral compound. That means pure enantiomer of R, specific rotation of R enantiomer of 2-bromobutane is given minus 112.0. So we know both this quantity and this quantity, so we can get the enantiomeric excess or optical purity of our sample. So let's put all these values. So the observed rotation is minus 82.88, and the optical rotation or the specific rotation of pure compound, pure R enantiomer, is minus 112.0. Now so the enantiomeric excess will be just 74%. That means in our sample or in our given solution of 2-bromobutane, 74% R enantiomer is present. Now the rest means 100 minus 74, which is 26%, is in the racemic mixture. That means racemic mixture is the equal percentage of R enantiomer and S enantiomer. So in our given solution, 74% R enantiomer is present, and rest 26% is in racemic mixture. That means equal percentage of S enantiomer and the R enantiomer. That means 13% both. Now racemic mixture is actually optically inactive. It is optically inactive. That means it contains actually equal percentage of R and S enantiomer. So that's why let's say the R enantiomer rotates the counterclockwise direction, rotates the plane of polarization in the counterclockwise direction, and let's say the S enantiomer rotates the plane of polarization in the clockwise direction. So in case of racemic mixture, since the equal percentage of both S and R enantiomer are present, so that's why both the rotation will cancel out each other. So the racemic mixture will not rotate the plane of polarization net. So there is no net rotation of plane of polarization in case of racemic mixture. So that's why the racemic mixture is optically inactive. Now let's get back to the question. So the question asks the percentage of S enantiomer present in the given sample. So we in the last slide we can see that the percentage of S enantiomer present is 13%. So the answer is 13% here. Now for further details on this topic, you can visit the lecture series on symmetry, stereochemistry and applications, and the instructor is Professor Anshuman Raichaudhuri from Aizan Mohali. So any doubts from this question? All clear? Okay, so okay, great. So do you guys know why any chiral compound actually show this type of property, like rotates the plane of polarization? Anyone? Okay, so let me just tell you in one line. So basically what is plane polarized light? We can think of plane polarized light as a combination of two helical circularly polarized light. That means that is the clockwise two circularly polarized mean one is rotating clockwise direction and another is rotating counterclockwise direction. So plane polarized light is basically a combination of two helical or two circularly polarized light. Now if our given sample or solution contain a particular chiral compound, let's say R or S, so R enantiomer, so this particular enantiomer will interact with both this circularly polarized light differently. That means let's say R enantiomer favors the left circularly polarized light, or S enantiomer favors the right circularly polarized light. Let's just assume that. So the interaction between this electromagnetic field, that means polarized light, and the given compound, chiral compound, is different. So this is why the velocity of light when we pass any kind of plane polarized light through a given compound is different. So that means one moves ahead over another. So that's why a given chiral compound actually rotates the plane of polarization. So this is a short explanation of the optical rotation. Okay, so if everything is clear, then we can move to our next question. So this is question number 53 from 2019 chemistry paper, and this is about the quantum chemistry, quantum mechanics, operator algebra, etc. So the question says, if now an operator expression is given, so then where Sx and the Sy are the spin angular momentum operators, and here alpha is the spin up eigenfunction. Now we have to find out the value of A here, this A, round it up to the 1 decimal place. So let's first look at some of the basics of operator algebra, most precisely the angular momentum operator algebra. Now I will be briefly discussing on this angular momentum operator algebra in terms of orbital angular momentum, and the operator algebra for the corresponding spin angular momentum is similar, so we can get from this. So Lx, Ly and Lz are the three components of the angular momentum, orbital angular momentum. L, let's say orbital angular momentum is L. So in Cartesian coordinates, the Lx operator can be represented by this expression, and Ly is represented by this, and Lz is represented by this. Now the total angular momentum, which is the total orbital angular momentum in this case, which is capital L. Now square of the total orbital angular momentum, which is L square, we can represent it by L square equal to Lx square plus Ly square operator plus Lz square operator. Now in polar coordinates, that means in the r, theta and phi space, so Lx operator, that means the x component of angular momentum operator, is represented by this expression, and then y component of angular momentum operator is represented by this expression, and the z component angular momentum operator looks like this. So this is actually important, like z component of angular momentum equal to minus I h bar, or h bar divided by I del phi, and here h bar is the h over 2 pi and h is the Planck constant. So the total square of total orbital angular momentum, which is basically L square operator, is represented by this expression, and we can see this square of L square operator while solving the hydrogen atom problem in quantum mechanics. Now this is the some commutation relation between these two operators, these three operators. Commutation relation means, let's say we have an operator A, another operator B. So commutation relation between these two operators is represented by the third bracket of A and B, A comma B, which means A operator multiplied by B operator minus B operator multiplied by A operator. So AB commutator means A times B minus B times A. So the commutation relationship between the x component of angular momentum, orbital angular momentum, and the y component of orbital angular momentum is I h bar Lz operator, and that means I h bar times z component of orbital angular momentum. Similarly, Ly Lz commutation relation is I h bar Lx, and Lz Lx commutation relation is I h bar Ly. Now the commutation relationship between the any component of orbital angular momentum, it could be Lx, Ly or Lz, with the square of total angular moment, orbital angular momentum, that means L square, is 0. Now any commutation relation 0 means we can measure the observable corresponding these two operators simultaneously. So any commutation relation 0 means we can measure the observables of these corresponding to these two operators simultaneously. Now this is the eigenfunctions of the z component of angular orbital angular momentum. Here Lz is an eigen operator of spherical harmonics. Why Lm is the spherical harmonics? Then means the angular part of our wave function, orbital wave function. And if we operate Lz to the spherical harmonics, then we can get the eigenvalue m times h bar, where m is the magnetic quantum number, and eigenfunction will get back, like spherical harmonics will get back. So also the L square operator has the eigenvalue similarly L into L plus 1 h bar. So these two are important for another questions maybe. Now the operator angular momentum operator algebra for the corresponding spin angular momentum, or Sx, Sy, Sz in this case, are similar to the orbital angular momentum. That means the commutation relationship are also similar. Sx commutation relation with Sy will be I h bar Sz. Similarly, all three we can write down. Now the sz operator eigenfunction, if we operate the z component of spin angular momentum, that means sz with any spin eigenfunction. So for electron, let's consider the case of electron. We know the spin angular momentum quantum number, capital S, is half. That means ms will be equal to, possible values of ms will be equal to minus half and plus half. That means only two possible spins are there for electron. One is we call it, one is up spin and another one is down spin. So let's say the up spin, which is plus half, is alpha, and down spin, which is minus half, let's say it is beta. So if we operate the z component of spin angular momentum, that means sz with alpha or beta, the eigenvalue for this case will be just ms times h bar. Now for alpha, ms value is plus half, so plus half times h bar, and you can get back the eigenfunction, which is alpha. Now if we operate sz with beta, that means down spin eigenfunction, the eigenvalue will be similar, ms h bar. Ms here in this case, ms is minus half. We can get back the eigenfunction beta. So these two relations are important. So basically, if we operate sz with any of alpha or beta, we can get the eigenvalue ms times h bar, where ms is the magnetic quantum number, spin quantum number, and possible values of ms for electron is minus half and plus half. Okay, now let's get back to the question. So this operator expression is given. So basically alpha is the spin up eigenfunction here, sx is the x component of spin angular momentum operator, and the sy is the y component of spin angular momentum operator. Now let's just focus only this term, sx sy minus sy sx. So we have seen in the previous slide that any commutation, any relation between the like AB minus BA, or Sx Sy minus Sy Sx will be the commutation relation of Sx and Sy, right? So commutation relations of Sx and Sy will be just I h bar time Sz, we have seen in the previous slide. So let's just put I h bar Sz here. So just alpha or Sz alpha. So now let's just do this part. So basically it will be alpha I h bar Sz operator alpha. Now I h bar is the constant term, I is constant and h bar is constant value, so we can write down here like, so I h bar times alpha Sz operator and alpha. Now let's just focus on this part. We are operating Sz operator on spin up eigenfunction, so that means it will give as ms h bar. So ms means half in this case, that means spin up eigenfunction ms is half, so half times h bar. So I h bar times half h bar, this is both are constant, so that's why we are writing down here outside of this bracket, then alpha, then alpha. Now alpha is the spin up eigenfunction, no? So alpha is orthonormal and wave function. So orthonormal means they are orthogonal and normalized. Normalized means alpha will be equal to 1. So this is called the Dirac bracket. So alpha Dirac bracket will be equal to 1, and this is the normalized condition, and orthonormal means alpha beta bracket will be equal to 0. So in this case it is alpha. So as the spin up wave function alpha is normalized, so that means it will be equal to 1. So let's just do this, I h bar times half h bar times 1. So I h bar square times half. So the relationship is given I h bar square a. So a means in this case it will be half. Now half rounded up to 1 decimal place means it is 0.5. Now for further details on this topic, you can visit the lecture series on the introductory quantum chemistry. Instructor is Professor K.L. Sebastian from IISc Bengal. So any doubts on this question? Okay, everything is clear, I think. Okay, so now let's just move to our next question. Question number 55 from 2019 paper. So here the question is, consider a two-dimensional harmonic oscillator with angular frequency omega x equal to 2 omega y equal to 6.5 times 10 to the power 14 rad per second, and the wavelength of the x polarized light required for the excitation of the particle from its ground state to next allowed excited state is like some x times multiplied of 10 to the power minus 6. So speed of the light is given here. So it is the problem about two-dimensional harmonic oscillator and the angular frequency of x direction, that means omega x, and the y direction is given, and the relationship between the omega x and the omega y is given, which is the omega x equal to 2 omega y equal to 6.5 times 10 to the power 14 rads per second. And also the wavelength of x polarized, so we have to find out the wavelength of incident light, wavelength of light. Now the x polarized is important, that means it only excites the harmonic oscillator corresponding to the x direction. The y direction harmonic oscillator or y direction states will not be disturbed, so that's why the x polarized is written there. So we have to find out the wavelength corresponding to the x polarized light which is required to excite a particle from its ground state to next allowed excited state. Okay, so let's first look at some of the basics of simple harmonic oscillator. So simple harmonic oscillator are in short SHO, which follow the Hooke's law, like where force, where F is the force, is proportional to the displacement. We all know that. So force is proportional to the displacement, which is the x minus xc. That means the displacement of the coordinate from the equilibrium value. Xc is the equilibrium position. And this minus sign is important here because it is representing the restoring type of force. That means if you go further away from the equilibrium, then the force will be greater and greater, and it will pull you back to the equilibrium position. So that's why it is minus sign, and that means it is restoring type of force. Now from this we know that force is the for conservative system, force is the derivative of potential energy function. So F is the minus of dvx dx equal to minus, so let's just proportionality constant is k, so k is the force constant. So from this relationship, minus dvx dx will be equal to minus k times displacement. The minus sign will cancel out each other, so dvx dx will be k times x minus xc. Now you can get from this equation, we can get the potential energy function, which is the Vx equal to half of k times displacement square. Now in this case, in this equation, k is the force constant, and xc is the equilibrium position, as I told, and the we know the omega angular frequency is root over of k over m, where m is the mass of the oscillator. So the potential energy, another way of representing this, is the half of m omega square x minus xc square. Okay, now the quantum mechanics of SHO, 1D SHO. So we know if we solve quantum mechanically the SHO problem, we can get the energy eigenvalue of harmonic oscillator. So energy eigenvalue we represent it is En equal to n plus half h bar omega, right? So here n is the quantum number, and in this case the quantum number n can vary from 0, 1, 2, 3, 4 like this. H bar is the h over 2 pi, h is the Planck constant, and here omega is the angular frequency. So this is the expression of energy eigenvalue for nth quantum number. Now we know for harmonic oscillator the allowed values of simple harmonic oscillator, or allowed values of transition, allowed transition is where change of quantum number, that means delta n, will be equal to plus minus of 1. Only for this case the transitions for simple harmonic oscillator is allowed. That means from 0 to 1 transition is allowed, but 0 to 2, in this case delta n will be equal to, for 0 to 2 delta n will be equal to 2 minus 0 equal to 2. So this is not plus minus of 1, so this transition is not allowed, it is forbidden transition. 0 to 3 is not allowed, but again 1 to 2 is allowed, because here in this case delta n equal to 1 plus 1. Again 2 to 3 is allowed, 3 to 4 is allowed, like this. So basically the take home message is the allowed transition for simple harmonic oscillator is delta n equal to plus minus of 1. Now I am not here going into the details of why this is case. If you want to know, you can ask. Now so the allowed transition is condition for allowed transition is delta n equal to plus minus of 1. Now for 2D harmonic oscillator, let's say it is uncoupled, that means one along x direction there is an harmonic oscillator, and along y direction there is an harmonic oscillator, and the two oscillators are not coupled. So in that case the energy eigenvalue will be, for x direction, nx plus half times h bar omega x. Let's say nx is the quantum number along x direction harmonic oscillator, and omega is the angular frequency of the x harmonic oscillator, and plus ny plus half times h bar omega, and ny is the y direction quantum number, and the omega y is the y direction angular frequency. Now in the question it is said that we are using x polarized light. That means only the harmonic oscillator along x direction will be excited. The y direction harmonic oscillator will not be disturbed. So from ground, now it is also asked for from ground state, that means n equal to 0, or for harmonic oscillator ground state is n equal to 0, and next allowed transition. Now what is the next allowed transition? What will be the next allowed transition? N equal to 1, because in this case only delta n will be equal to plus 1. So that means nx equal to 0 to nx equal to 1, and y harmonic oscillator will not be changed. So that means let's say the quantum number along y direction is ny. It is fixed. It will be fixed. So delta E, that means change in energy, will be E1 ny. Let's say so 1. We are exciting to 1, nx equal to 1, so nx equal to 1 times comma ny is fixed, minus E0 ny, that means nx equal to 0 comma ny. So this will be the change in energy due to excitation. Okay. So change in energy delta E will be just this, and the delta E, so let's just compute this. So E1 ny means you can put nx equal to 1 here, so 3/2 h bar omega x plus ny plus half h bar omega y minus then E0 ny means you can put ny equal to 0, so that means half h bar omega x plus ny plus half h bar omega y. Now these stuff will cancel out each other, so it will be just 3/2 h bar omega x minus half h bar omega x will be equal to just h bar omega x. So change in energy due to excitation will be equal to just h bar omega x for 0 to 1 transition. Now omega x is given, that means 6.5 times 10 to the power 14 rad per second. Now we also know that delta E is h nu, that means Planck constant times frequency of the light. So delta E here in this case it is h bar omega x. Now h bar means h over 2 pi omega x, which will be also equal to h nu, that means or nu equal to c by lambda. Nu frequency equal to speed of light c divided by wavelength of the light lambda. Now let's just focus on these two expressions, So h over 2 pi times omega x equal to h c by lambda. Now h will cancel out each other, so lambda will be equal to 2 pi c by omega x from this relation. Now we know the speed of light c, we know the value of omega x, so we can put all these. So 2 pi times 3 into 10 to the power 8 divided by 6.5 into 10 to the power 14. So lambda will be equal to 2.898 times 10 to the power minus 6 meter, because c is in meter per second and omega x is the rad per second and 2 pi is radian, so the overall unit will be in meter. So rounded up to 1 decimal place means 2.8. If we round up to 1 decimal place, it will be 3, because 0.8 is greater than 5, like 8 is greater than 5. So the wavelength corresponding to the x polarized light for the excitation of a particle from its ground state to next allowed excited state will be 3 times 10 to the power minus 6 meter. So answer in this case it will be 3. Now for further details you can visit the NPTEL lecture series on quantum chemistry of atoms and molecules. The instructor is Professor EduUdr from IIT Bombay. Okay, so any doubts on this question? Okay, yeah, so lecture link will be shared by the NPTEL representative, I think. So lecture link means the video solution you are talking about, or the live session link? Nihal?
Video session.
Okay, the live session link will be uploaded in the Gate portal. Like you can see the previous the link for the previous session is also uploaded in the Gate portal.
Okay.
Okay. So I have uploaded this live session in the YouTube and provided the link here in the Gate portal. Okay, now if everything is clear, then so any doubts from this question or any 3 questions? Okay, then let's discuss the little bit about adsorption. God. Okay. Oh, the screen is not here. So can you guys hear me properly, because there is too much disturbance today.
Yes, sir.
Oh, okay, thanks. So let's first discuss the adsorption in the remaining time. So Adsorption process means basically the gas molecules adsorbs or interacts with the surface on a solid surface. So let's say we have a solid surface here, and here are some gas molecules. So gas molecules interacts or the adsorbs on the solid surface. So here in this case the solid surface is called the adsorbent, or the gaseous molecules is called the adsorbate. Now there are different models for adsorption, like a Langmuir adsorption isotherm model, Freundlich adsorption isotherm model, Bate isotherm model. So let's first discuss about the Langmuir adsorption model. Now before that, adsorption can be actually of two types, which is one is the fuzzy adsorption, and another one is the chem adsorption. Physical adsorption or chemical adsorption, what does this mean? So physical adsorption is basically the gas molecules just weakly interacts with the solid surface. That means the interaction force can be actually van der Waals types of force. And the chemical adsorption means the gas molecules first interacts with the solid surface, then it can actually chemical reaction can happen. Now let's say we have H2 molecule here, hydrogen gas, and it is solid surface. So physical adsorption means basically the H2 molecule or the hydrogen gas weakly interacting with the solid surface. That means it can be van der Waals type of interaction. Now for chemical adsorption, the gas molecule actually interacts with the solid surface first, then chemical reaction can happen. That means hydrogen molecule can actually dissociate, and hydrogen molecule can actually dissociate to form hydrogen atom. So this is called the chemical adsorption. So now first discuss the Langmuir adsorption model. So in this model, Langmuir adsorption model, in this model, surface is considered a homogeneous surface. That means there are no roughness, so only smooth surface is considered. Homogeneous means all the sides are equivalent to each other. There is no roughness or any scratch there, only smooth surface is considered. So first point is homogeneous. And then it was assumed that all the surface sides are equivalent. That means gas molecules can actually bind to any surface side. So all the surface sides are equivalent. Then it was assumed or approximated that the adsorbate molecules, that means gas molecules, are ideal in nature. That means there will be no interaction between the gas molecules. Suppose the one gas molecule is adsorbed in this site and another molecule is adsorbed in this site. So in this model, according to this model, there will be no interaction between these gas molecules here on the adjacent side. And also since all the surface sides are equivalent, so the heat of adsorption for gas molecule adsorbing to any sides will be equal for any gas molecule or for any site. So delta H, that the heat of adsorption, is same. And also the most crucial approximation is that in this model only monolayer adsorption is considered. That means the gas molecules only adsorbs on the solid surface on just by one layer. But in real life we know that the gas molecules can adsorb on multiple layers, so the monolayer adsorption is not a good idea. Now for Langmuir adsorption model, it is considered a chemical reaction is happening. Let's say the adsorbate is A, surface site is S, then there will be an equilibration between the A and S, and it will fall and it will form, and A is complex. That means the adsorbate surface complex. So, and the equilibrium constant is, let's say, Ka. Now how do you derive this surface coverage, that means theta? Now let's say first adsorption process, that means A plus S to AS. In this case the rate constant is, let's say, K1, and then the desorption process, that means AS to A plus S, back reaction. Let's say in this case rate constant is K2. Now in this case the rate will be equal to, just in this case the rate will be equal to K1 times adsorbate concentration, which is the partial pressure here, so K1 times PA times the concentration of the surface site here is, that it is surface site is number of surface sites present per meter square. Now for in this case it will be equal to just K2 times the AS complex, AS here. Now if from these two expression we can compute the surface coverage theta. So theta will be basically equal to just concentration of the surface site covered here, covered surface sites, that means let's say concentration of S, then concentration of S0, that means initial number of sites before adsorption. So we call this theta is the surface coverage. We call the surface coverage the fractional coverage, that means the fraction of surface covered due to adsorption process. So which is the surface sites, ratio of surface sites covered by the gas to the number of free sites present before adsorption. So S divided by S0. Okay, so now for Langmuir isotherm model, so theta will be equal to just K1. I am not deriving this, so K adsorption, let's say equilibrium constant Ka times P A, partial pressure of the adsorbate, plus 1 plus K Tm. So this is the expression for the Langmuir adsorption isotherm model. And now if you can plot this also, like theta with Pa, and the plot will be look like this. Now there is another type of adsorption isotherm, which is the Freundlich isotherm. For the Freundlich isotherm model, the theta surface coverage will be equal to some constant C times e to the power minus e to the power some another constant D times Pa. So this is also another type of isotherm, and if we log plot this, if we take log both sides, log theta will be equal to, sorry, this is the Pa. Theta will be equal to C times Pa times, okay, I forgot this expression actually. Okay, so let's now consider the Bate equation. Now this is the modification about the Langmuir isotherm model. So in the Bate equation, the multiple layer adsorption is considered, which is in the Reel's case, and let's say it is the surface side, and the gas molecules monolayer are adsorbed only as monolayer. Then other gas molecules can interact with these gas molecules and adsorb over each other. So it is the monolayer adsorption is considered here. Now the heat of adsorption between the first layer and the surface side. The surface side, let's say it is the delta H1, and heat of adsorption between the other sides, that means second layer and the first layer and the third layer and the second layer, are all equal, which is the heat of liquefaction. So in the bait isotherm model, the equation of surface coverage, or theta, will be equal to just 1 over V times 1 minus P0 divided by P, equal to C minus 1 times VMC P divided by P0 plus 1 over VMC. So this is the equation for the bait isotherm, and we actually discussed in the last class here. We solve a problem from this equation. Now if we plot this 1 upon V 1 minus P0 by P times P divided by P0, then we can get a straight line here. Now the intercept of the straight line will be equal to just 1 upon Vm divided by C, and the slope of the straight line is C minus 1 times VMC. Now from the slope and the intercept we can get the volume Vm, that means the volume of the monolayer coverage. So this is the bait equation. Okay, so today actually very disturbing, too much disturbance. Okay, so any doubts on this adsorption?
No, sir.
Okay. Sorry, today there is a little bit too much of disturbance going on. Okay, so next class we'll be solving another 3 questions, and basically we'll be discussing the quantum mechanics and the group theory, little bit of group theory. Okay, so if there is no doubts, then we can end this session. So everything was clear?
Yes, sir. Thank you, sir.
Yeah, thanks. So let's meet next week. Yeah, thanks. Okay, bye. I'm ending this session.